The purpose of this video is to define the inverse of a matrix. We'll discuss it, and then I will show you an algorithm to calculate the inverse of a square matrix. So let's begin by recalling something from a previous video, and that is that you cannot always cancel or divide when you're doing matrix multiplication. The simple example that we discussed before was of three matrices. All of them are 2 by 2, so we can multiply them together. A, B, and C. You can check that if you multiply the matrices A and C together, you get the same matrix as if you multiply the matrices B and C together. But just by inspection, A does not equal to B. So you can't really cancel C from this equation because that would lead to a contradiction. And what's happening here is that C is a matrix that does not have an inverse. The inverse of C does not exist. We would call C a matrix which is not invertible or singular. So let's define what it means for a matrix to have an inverse. A matrix is invertible if there exists some other matrix such that when you multiply them together, you get the identity matrix. So if your matrix is A, you need to be able to find some other matrix B such that both A times B and B times A gives you the identity matrix. And when you can find such a matrix, you can use the notation A inverse for B. Now, not all matrices are invertible. Some are invertible and some are not. Let's make an analogy to something very familiar, like the real numbers. So if you take any real number, for example 3 or the square root of 7, then their inverses exist. The inverse of 3 is 1/3. If you multiply 3 times 1/3, you get back 1. It's its multiplicative inverse. Square root of 7 also has a multiplicative inverse. It's 1 over the square root of 7. So all of these real numbers that are not 0 have inverses, but 0 does not have an inverse. So not every matrix has an inverse, and this is definitely going to be a distinction that we're going to need to explore. But one thing that we can say is that matrix inverses are unique. Let's talk about that a little bit. I'll write this down as a theorem. Inverses are unique. If A is invertible, it has a unique inverse, A inverse. And that uniqueness is why we can use the notation A inverse, because there's one and one only, A inverse. It's not ambiguous what that means. Well, why is this the case? Let's kind of explore why this would be the case. Suppose for a moment that matrix inverses are not unique. If it were not the case that matrix inverses were unique, then we could say, well, let's take a look at a matrix A. Maybe it has two inverses, B and C. Then what would be true about B and C? Well, it would be true that both A times B would be equal to the identity. And it would also be true that C times A would be equal to the identity, if they're both matrix inverses for A. But if that were the case, then we could do the following. We could write B as the identity times B. And then the identity is CA. So in parentheses, that would be CAB. But now the associative property of matrix multiplication tells me that this is the same thing as C times AB. But AB is the identity. So this is C times the identity, and that's equal then to C. But that tells me that B is equal to C. So they weren't really different. They were in fact the same matrix. So this right here is a quick proof for why inverses are unique. Okay, so we have the definition of a matrix inverse. It's another matrix where you multiply them together and you get the identity. Let's now see how to calculate the inverse of a matrix. And one thing to keep in mind is that this algorithm that I'm going to show you is bound to fail when the matrix cannot be inverted, when it's singular. So this algorithm is only going to work if we have a matrix that genuinely has an inverse, and then it will certainly find that inverse. I want to demonstrate this algorithm by way of example. And the specific example that we're going to look at is a 3 by 3 matrix. 1, minus 1, 0, 1, 0, minus 1, and minus 6, 2, 3. The numbers are, of course, rigged up so that the calculation is going to be really easy. So the first thing that we do is we splice together the matrix A with the identity matrix. And what I like to do is use a dashed line to keep the matrix A and the matrix I kind of separate. The next step that we do is actually many steps. And what we're going to do is Gaussian elimination until we have reached an augmented matrix of the form I dotted line something, I for identity matrix. And that something that appears on the right is going to turn out to be A inverse. So I am going to work out all of the steps of this next kind of macro step. Let's make a little space on the page. And as we work through this, keep in mind that all we're really doing here is Gaussian elimination. It's the same process that we use when we're solving a system of equations, and that's going to be what gives us a matrix inverse as well. So when we start, we have A augmented with the identity matrix. And we are going to be doing the process of Gaussian elimination. The strategy is to take the first pivot and to eliminate everything underneath that pivot, everything in the first column. And after we do that, we'll proceed towards the right. So the first row operation that I want to use is going to kill the one that I'm going to highlight in green. We're going to be killing this one. And the appropriate row operation for that is going to be minus row 1 plus row 2 into row 2. And that row operation will produce this. So not only have I modified that single entry that I'm trying to kill, but it also has a ripple effect down the rest of the row. And let me point out that as we replace row 2 with minus 1 row 1 plus row 2, that it also changes some of the entries in the identity matrix as well, including the one that I have highlighted here in green. That went from being a 0 to a minus 1. And so something is starting to show up on the other side of the dotted line. All right, let's continue on and eliminate our next victim. So our pivot at the top, which is a 1, is going to now be used to eliminate this minus 6. And the row operation that we're going to want to use will be 6 row 1 plus row 3 into row 3. And so here's that row operation. All right, I'm continuing to highlight entries that show up to the right of the dotted line for emphasis. You'll notice that in our first row operation, it was a minus row 1 plus row 2 into row 2. The multiplier was a minus 1 here. And that's what showed up off the diagonal. The multiplier in the second row operation was a 6, and this also shows up now here in what used to be the identity matrix. And we have accomplished killing the second and the third entries of the first column. So we're going to continue on with our row operations, and the next target is going to be this minus 4. The row operation that we're going to write down then will be 4 row 2 plus row 3 into row 3. And at this point, we've actually produced something which is upper triangular. I've highlighted the diagonal in pink, and we have an upper triangular matrix. But we're not done. We need to continue pushing the row operations. So even though we would probably be able to read like the solution of a system of equations from a form like this, we're going to keep going. We want to now start using this entry as our pivot to eliminate the entries that are above it, and then continue from right to left. The next row operation that I'm going to do is just to turn this minus 1 into a positive 1, so it's only going to affect row 3. And so that next row operation I will put here. Let's align it kind of in the middle of the page. Minus 3 row 3 into row 3. That's just going to flip the signs on the last row, turning this into a 1 and a minus 2, a minus 4, and a minus 1. And then I'm going to use that 1 to eliminate the negative 1 above it. So I'll be taking row 3 plus row 2 into row 2. Here's the row operation and its effect. And then you'll see that I have just one more row operation to do. The last entry that I need to get rid of in the matrix that appears to the left of the dotted line is just this minus 1. After that, I'm going to be left with 1s down the diagonal and 0s everywhere else. So my very last row operation will be row 2 plus row 1 into row 1. And now I've got something that looks great. What I see when I look at this is I have 1s down the diagonal and 0s everywhere else. This means that this is now the identity matrix. See, I started out with the identity on the right, But how I know I'm done is the identity shows up on the left. So if A was on the left, then A inverse is what shows up on the right. So here is my A inverse, and my algorithm is complete. This was all there was to it. We just used Gaussian elimination, but let me convince you further that we actually produced A inverse. We should check our work. And in fact, you know, if you're in a homework or an exam setting and you've applied this algorithm to find the inverse of a matrix, it's always a good idea to check your work provided that you have the time. So this is how you would check the work that you just did. So I'm going to make a little space over here, and I'm going to check that my answer was valid. So what is it that makes a matrix the inverse of another matrix? You need to multiply them together to be able to get the identity matrix. So we're going to take our original matrix A, and we're going to multiply it to what we produced and see that we get the identity matrix. So we're going to be looking at A inverse, and we want to know, does this equal the identity? So here's our A, and let's take our A inverse that we just found. Let's make it look like a matrix. One of the things that's nice about using a tablet for these types of calculations is you make fewer transcription errors, but one of the things that you will do carefully when you write things on paper is make sure you are very careful with writing down numbers and getting the signs right. So let's multiply these two matrices together. Make sure we get the right thing. All right, so this is going to be some dot products. The first entry in this product, zooming in, is going to be calculated by row 1 dotted with column 1. So that gives us a -2 plus a 3 plus 0. And that is in fact a 1, which is exactly what we wanted to get. All right. The next entry is going to be formed by row 1, which is already highlighted in green. Let me do a little color coding here. Dotted with column 2, and that's going to give us this entry. All right, so we have -3 plus 3, that's 0, and then plus 0, and that gives us a 0, just as desired. The next entry is going to be formed by, again, our green row, dotted with the third column. Let's use yellow to produce this entry. And we see we get a -1 plus 1 plus 0, and indeed that is 0. When you go to calculate the entries for the second row, you're going to be using the second row of A and then the 3 columns from A inverse. And this is more dot products to work out. You should check these next 2 rows to be sure you're comfortable with matrix multiplication, but it is going to work out to be 0, 1, 0 and 0, 0, 1. So AA inverse did work out to be the identity matrix, and we have a good check on our work. In the next few videos that I record, I will be demonstrating the calculation of a matrix inverse in several different ways.